parameters of antenna. The topics are going to be like this: gain, directivity, effective aperture, radiation resistance, bandwidth, input impedance, and those things we have discussed. So in the previous class, those topics were discussed, and few topics I didn't tell you. The topics are going to be polarization, effective aperture, and antenna temperature. Okay, coming to the point of polarization. Polarization is nothing but orientation of electric field with respect to earth is going to be called as polarization. So we have a wide variety of polarization. We have one is going to be called as linear polarization and inclined polarization. In linear polarization, we have horizontal polarization and vertical polarization. Okay. Um, and just we have the recap of the previous topic, and then we will enter into the antenna array concept. Later on, we will go for the antenna today's topic, antenna arrays topics. So the previous class we discussed the basic fundamental parameters and dipole and monopole antenna. Okay, wow. Now we will see the brief introduction about the previous topic, and then we will go to the antenna array concept. Okay. Now we will discuss what is antenna. So you all know that the antenna is going to be nothing but an ordinary elevated conductor which radiates and intercepts the electromagnetic energy. It's going to be called as antenna. And also we can say that our antenna is going to be a sensor, transducer, impedance matching device with extensive application in all communication, radar and medical system. So in the previous class, we have discussed about what is wired communication and wireless communication. So we have seen what is wired communication and different types of wires available in the previous class. So from the open wire to optical fiber communication, we discussed. That's what about your wired communication. Now coming to the point of wireless communication, your antenna will be acting as a major part in the case of wireless communication. That means there is no antenna, that means no antenna, sorry, in wireless communication, antenna placing a vital role. So antenna acting as a major component in the case of wireless communication. Okay. Next, we'll see about the properties of antenna. Properties are going to be identical impedance, identical direction coupler, same effective length or height. It's going to be called as major concepts of properties of antenna. Okay. And also we discussed about the fundamental antennas, like three types we discussed. The very first one is going to be called as isotropic antenna. Second one, directional antenna. Third one, non-directional antenna. Okay. So while coming to the point of isotropic antenna, the isotropic antenna which will be radiate equal towards in all direction, it's simply going to be called as hypothetical lossless antenna. Generally, we'll take this antenna for the reference antenna. Okay, wow. Next, we'll have the directional antenna. It is the one having the properties of radiating and receiving waves effectively in some other direction than in other direction. It's going to be called as directional antenna. And that means it will radiate the energy and receive the energy towards a particular direction. It's going to be called as directional antenna. And third one, non-directional antenna. Non-directional antenna, the radiation will be happening towards in all the direction. It's going to be called as non-directional antenna. And coming to the point of antenna parameters, I told you the very first parameter is going to be radiation pattern. Okay. So in this case, you have to concentrate about your two types of pattern. One is going to be called as field pattern. Another one is going to be called as power pattern. Okay. In case of power pattern, in case of field pattern, the radiation is expressed in terms of field strength. Is going to be called as field pattern. Okay. Next, we have the power pattern. The power pattern is nothing but and you have to know about your beam solid angle and beam area. Okay. So in case of beam solid angle and beam area, 1 steradian equal to 1 radian square. Okay. So the angle produced by the circle is going to be called as radian, and the angle produced by your sphere is going to be called as steradian. Therefore, 1 steradian equal to 1 radian square. Okay. This thing you have to know. Okay. The very first parameter what I told you, antenna parameter, in which you have to know about your beam width. So beam width, we have the half of beam width and first node beam width. Both you have very important things. And second one, you have to know about the beam solid angle. And coming to the point of types of radiation pattern, we have two types: field pattern and power pattern. In case of beam solid angle and beam area, in case of beam solid angle and beam area, so I told you 1 radian equal to 1 radian square. And coming to the point of next parameter, beam efficiency. Beam efficiency is equal to major beam area by minimum beam minor beam area. Okay. Next, the important parameter, second one, radiation intensity. It's foremost important parameter of antenna. It is defined as the ratio of power radiated from an antenna per unit solid angle. Once again, it is defined as the ratio of power radiated from an antenna per unit solid angle. Is going to be called as radiation intensity. And by notation, we can give it as U. U of theta comma phi. We can also give as U of theta comma phi equal to power radiated from antenna by unit solid angle is going to be called as radiation intensity. Okay, that's what about radiation intensity concept. And also the radiation intensity of isotropic antenna equal to U equal to P rad by 4 pi. P radiation by 4 pi. The unit is going to be watts per steradian. Okay. The third parameter. What is the first parameter? Radiation pattern. Second one, radiation intensity. Third one, gain. Gain of the antenna. Gain of the antenna can be described in terms of radiation intensity, radiation of power received, and radiation intensity in terms of field strength. Okay. Next, we have the directive gain and power gain. While coming to the point of gain of the antenna. Okay. And coming to the point of next parameter, antenna efficiency. Antenna efficiency is equal to power radiated by total power. Simple. Antenna efficiency is equal to power radiated by total power is going to be called as antenna efficiency. Okay. Next we have directivity D. So directivity also an important parameter is defined as the ratio of maximum radiation intensity to the average radiation intensity of an antenna. It's going to be called as directivity. So directivity D equal to maximum to by average. Directivity D equal to U max by U average is going to be called as directivity. And directivity of an isotropic antenna is going to be equal to 1. Keep in your mind. In the previous class also I explained you what is directivity of isotropic antenna. Definitely they will ask in the gate question. Directivity of isotropic antenna D equal to 1. Okay, wow? The problem also we have seen in the previous class. So later on we have discussed about the concept like bandwidth also we discussed, and the concept of yeah, I forgot to tell you FBR, front to back ratio. FBR equal to power radiated in desired direction by power radiated in opposite direction. It's going to be called as front to back ratio, FBR. Very important ma, front to back ratio. Okay, wow? These are the parameter, and also we discussed about the monopole, dipole antenna and half wave dipole antenna. Okay, and how the radiation is going to be happening from dipole antenna and monopole antenna also we discussed. Okay, with this we discussed the topics in the previous class. Okay, with this basic information we'll move to the next topic what we are going to take today. Okay, the topic is going to be antenna arrays. Okay, next one we are going to see about what is antenna array concept. Okay, antenna array concept. Yeah, 1 second. Yes. Now we'll see about the concept of antenna array concept. Yeah. So what do you mean by antenna array? Yes, what is antenna array? Do you have any idea about antenna arrays? Do you have any idea about antenna arrays? Yeah, I'll tell you. Nothing but it's a system, keep in mind, it's a system of similar antennas oriented similarly to get greater directivity. So whatever it may be, whatever the antenna we are going to take, it should have the maximum directivity and maximum gain. Then only the antenna is going to be using for the various applications. For various communication, we use those antennas. Okay, wow? Definitely. Antennas gain and directivity should be always maximum when compared with other one. Other one is something but reference antenna. What is reference antenna? Your reference antenna is something but hypothetical lossless isotropic antenna. Okay, va? So whatever it may be, whichever the antenna you're going to take, the antenna should have the greater directivity and greater gain. For that, we need to design a antenna array concept. Antenna array concept. Once again, I'll tell you what is antenna arrays. Yeah, it is a system. It is a system of similar antennas oriented similarly to get greater directivity. Is going to be called as antenna arrays. Okay. Yeah. It may also be defined as radiating system consisting of several spaced and properly phased radiators. Yeah, we can also say it as, it may be also defined as radiation system constituting of several spaced and properly phased radiator is going to be called as antenna array concept. Okay. Okay. Now we'll see about the basic concept here. The radiation pattern of a single element is relevant width and each element provides low value of directivity. In many applications, it is necessary to design antennas with very directive characteristics to meet the demand of long distance communication. Yeah. So we all know that our signal is going to be propagated in terms of electromagnetic waves so that it should be reached towards our long distance. So not to reach for long distance, the signal gain and directivity should be always maximum. This can only be accomplished by increasing the electrical size of the antenna. Higher directivity is a basic requirement in point-to-point communication, radar and space. Okay. Enlarging the dimension of single element often lead to more directive characteristics. Another way to enlarge the dimensions of the antenna without increasing the size of the individual elements is to form an assembly of radiating element in an electrical and geometric configuration. This new antenna formed with multi-element is referred to as antenna array. Keep this point in your mind. Okay. This new antenna formed by multi-element is referred to as an array. Okay. In most cases, the elements of an array are identical. Thus, antenna array can be defined as a system of similar antennas directed to get required high directivity in the desired direction. So this point more important, ma. Thus, antenna array can be defined as a system of similar antennas directed to get greater high directive in the desired direction. Okay, va? Next, the antenna array is said to be linear if the elements are antenna are equally spaced along a straight line. Okay. General types we have the linear antenna and uniform linear. Keep in your mind, ma. Keep in your mind the general types of antenna array is going to be called as linear array and uniform linear array. Now we'll see what is linear array. An antenna array is said to be linear if the individual antennas of an array are equally spaced along a straight line. Okay, va? An antenna array is said to be linear if the individual antennas of an array are equally spaced along a straight line. Is going to be called as linear antenna. Okay, va? This is what about your linear antenna. And coming to the point of uniform linear array. Okay, we have two forms, ma. One is going to be called as linear array. Second one, uniform linear array. The uniform linear array is one in which the elements are fed with current of equal magnitude with uniform phase shift along the line. The uniform linear array is one in which the elements are fed with currents of equal magnitude with uniform phase shift along the line. Is going to be called as uniform linear array. Okay, va? Now coming here, we'll see that. Yeah, it's said to be uniform linear array if all the elements are fed with current of equal magnitude with progressive uniform phase shift of long line. It's going to be called as uniform linear array. First one is linear. The antenna is said to be linear if the elements of the antenna are equally spaced along a straight line. Okay. Next, 5 controls used to shape the overall pattern of the antenna. One is geometrical configuration of the overall antenna, linear, circular, rectangular, spherical, etc. Relative displacement between the elements. Okay, now these points. Types of antenna array I told you. So before we are going to see about the types of antenna array, now we'll see the types of antenna array basic concepts. How the antenna arrays are going to be classified, on which basis of designing of the antenna. Okay, before we are going to see about the type of antenna, we'll see the basic fundamentals of antenna types. Okay, first one, based on geometry configuration. Based on geometry configuration, the antennas are going to be divided into three types. One is linear, planar, and conformal. Yeah, next, based on current excitation, the antenna array is going to be classified into two types: broadside and end fire. That's what here we are going to see. Next, third one, based on elements, we have two types: parasitic and non-parasitic elements. Okay. Fourth one, based on amplitude distribution, we have the four types: uniform, binomial, edge, and optimum. Uniform, binomial, edge, and optimum. And last one, fifth one, based on types of input-output signal. Based on types of input output signal is going to be called as phased array, retrodirective or self-focusing array, and finally we have the adaptive array. Once again, I'll tell you how basically we can classify our antenna arrays. One, based on electromagnetic configuration, we have three types: linear, planar, conformal. Second one, based on current excitation, broadside and end fire. Third one, based on elements, parasitic and a non-parasitic element. Fourth one, based on amplitude distribution, uniform, binomial, edge, and optimum. Okay. And fifth one, last one, based on types of input output, it's going to be classified as phased array, retrodirective array, and adaptive array. Okay. So these are the basic configuration. Now we can view our in the slide. Practically, various forms of antenna array are used as radiating system. Practically, various forms of the antenna array are used as radiating system. They are broadside array, end fire array, collinear array, and parasitic array. Okay. Actually, we are going to see in the syllabus of these four types. Okay. Broadside, end fire, collinear, and parasitic array. Okay. BSA means broadside array. EFA means end fire array. Okay. Hope you understood. Okay. Generally, we have the four types of antennas. Okay. Broadside, end fire, collinear, and parasitic array. Okay. Now coming to the point of broadside array, the number of identical parallel antenna are set up along a line is going to be called as broadside array. It's going to be viewed in the form in the case of figure 1. Okay. Yeah. This figure will tell you what is broadside array. Okay. So this what the center one is going to be called as antenna axis of the antenna array. So individually we are going to feed in the different types of antennas. So these are all going to be called as antennas. Okay, having the distance of D. Okay, A0 to A6, 7 antennas, and D is going to be distance between the two antennas. So here we have the maximum radiation. Okay, so now you see about your broadside array concept. Yeah, the number of identical parallel antennas are set up along a line. In BSA, in broadside array, the individual antennas are equally spaced along a straight line, and each element, okay, is fed with current of equal amplitude all in the same phase. Okay. So once again, a broadside array consisting number of identical antennas placed parallel to each other along a straight line, and the direction of maximum radiation is always perpendicular to the plane consisting of elements. So this perpendicular is going to be called as figure of 8. Keep in mind, broadside array will radiate the energy in the form of figure of 8 direction. Okay, va? Next, this is about your antenna, broadside antenna concept. Now we go to the point of end fire. Now in the case of end fire, in end fire, the number of identical elements are fed with current of equal magnitude, but their phase varies progressively along the line in such a way as to make this entire arrangement unidirectional. Is going to be called as end fire array. Okay, so this is what about your end fire array concept. So maximum direction here is going to be perpendicular. Sorry, there is going to be perpendicular. Here it is going to be coincidence with the angle. Antenna axis angle, it will be coincidence. Okay, va? So D is the distance between the two antennas, and A0 to A4 is going to be antennas. A0, A1, A2, A3, and A4 is going to be called as antennas. Okay. So the main thing you have to understand, in broadside array, the radiation will be happening towards the perpendicular direction. But in the case of end-fire array, the radiation is going to be happening in the case of, it will be coincidence with the antenna array axis of antenna array. It's going to be called as end-fire antenna. Once again, we'll see what is end-fire. The end-fire array is very much similar to the broadside array from the point of view of arrangement, same point of view. But the main difference is the direction of maximum radiation. Yeah, there is going to be perpendicular, here it's going to be coincidence with the antenna parameter. In broadside array, the direction of maximum radiation is perpendicular to the axis of array. Correct? In broadside array, the direction of the maximum radiation is perpendicular to the axis of array. And next one, while in the end-fire array, the direction of the maximum radiation is along the axis of an array. Keep this in mind, ma. Along the axis of array. Okay. These are the main difference between your broadside and end-fire array. So in broadside, all the antennas are fed equally with currents of equal magnitudes, but their phases vary progressively along the line to get entire arrangement unidirectional finally. Unidirectional finally. That is maximum radiation along the axis of the array. Okay, it's going to be called as available in the figure 2. Thus, end-fire array can be defined as an array with direction of maximum radiation coincides with the direction of the axis of array to get unidirectional radiation. Okay, va? Next, third one, collinear array. Okay, here we have vertical and horizontal collinear array. There, in broadside array and collinear array, the antennas are going to be equally spaced. Okay, va? But here, in the case of collinear array, we are going to place the antennas one by one. Either it is going to be vertical or horizontal. We are going to place the antennas one by one. So, the length of the antenna is going to be very wider in the case of collinear array than compared with our broadside and end-fire array. Can you able to get it? The antenna length is going to be short in the case of broadside and end-fire array, but in the case of collinear array, the length of the antenna is going to be more. Okay, va? Here now we will see what is collinear array. Okay, as the name indicates, in the collinear array, the antennas are arranged coaxially. Keep this in mind, coaxially. That is, the antennas are arranged end to end along. End to end along a single line as shown in the figure A and B. Yeah, this one vertical end to end connection. This antenna axis end to end connection. This horizontal end to end connection. So this one is, so in this case, the radiation will be happening towards all the direction. Here it is going to be vertical like this, downward shape. In case of horizontal, we can get the figure of 8 in the case of horizontal. Figure of 8 horizontal, downward shape in the case of vertical collinear array. Okay. Yeah. Now we'll see. The individual elements in the collinear array are fed with current equal in magnitude and phase. Once again, ma. The individual elements in the collinear array are fed with current equal in magnitude and phase. This condition is similar to the broadside array. In collinear array, the direction of maximum radiation is perpendicular to the axis of array. It's going to be called as collinear array. So these are the shapes. Vertically arranged here, horizontally arranged here. Okay? Here, vertically arranged here, and here it is going to be horizontally arranged. Both are by means of the coaxial cable. Okay? This is for collinear array. So the radiation pattern of the collinear array and the broadside array is very much similar, but the radiation pattern of the collinear array has circle symmetry with main globe perpendicular everywhere to the principal axis. Thus, the collinear array is called omnidirectional array of or broadside array. And we can get maximum. The gain of the collinear array is maximum if the spacing between the elements is of the order of 0.3 to 0.5 lambda. This point very important, ma. If the distance between the antenna is going to be between 0.3 and 0.5, we can get more gain when compared with other antennas. And last one, parasitic antenna. So the last one, parasitic antenna. In order to overcome feeding problem, there individual antenna should feed in 3 cases: broadside, end fire, and colony. In 3 cases, individual antenna should be feeding properly. That problem is not available in case of parasitic array. In order to overcome feeding problem of the antenna, sometimes the elements of the array are fed through the radiation from the nearby element. The array of antenna in which the parasitic elements get the power through electromagnetic coupling with the driven element in proximity with the parasitic element is known as the parasitic array. It's going to be called as parasitic array. The simplest form of the parasitic array consists one driven element and one parasitic element. In multi-element parasitic array, one or more driving element are fed. Also, one or more parasitic element. In general, the multi-element parasitic array, at least one driven element and one or more parasitic element is going to be called as parasitic antenna. Okay. The best example of the parasitic array is going to be called as Yagi-Uda antenna. Okay, va? Yagi-Uda antenna. Okay. This antenna is useful to receive the television signals. Okay. Older days we use this antenna, Yagi-Uda antenna. Yagi-Uda antenna, or simply we can call it as Yagi antenna. Yagi antenna or Yagi-Uda antenna. Here in this you can see that we have number of antennas. One is going to be called as dipole. This one. The circular one is going to be called as dipole. Second one reflector. Followed by all is going to be called as director. So we have the dipole, we have the reflector, and we have the director. Okay. So we have driven element. We are not going to give feeding all the antennas. We are going to feed only for the dipole, from where the energy is going to be propagated towards the reflector. The signal will be sent towards your director. Through the director, it will reach the receiving end. Okay, va? So here director only we are going to feed the antenna, not for the directors and reflector. Okay, listen ma. 1 second. Yeah, we are always going to feed the antenna of dipole antenna. We are not going to feed directors and reflector. The reflector and directors are helpful to propagate the waves. So we are going to feed only for dipole, not directors and reflector. This is what about the parasitic antenna, parasitic array or Yagi antenna. Okay. So older days we use this antenna for the reception of television signal. Okay, TV signal reception. We use this Yagi antenna. Okay. Yeah. Now we'll see about array of 2-point sources. Okay. The array of point sources is nothing but the array of an isotropic radiator occupying 0 volume for the greater number of point sources in the array. The analysis of antenna array becomes complicated and time consumption. Also, the simplest condition of number of point sources in array is 2. First we'll take 2. Later on we'll going to take about our n number of elements of our antenna source. Okay. Then conveniently analysis is done by the considering first 2-point sources which are separated by distance having same polarization. The results obtained for only 2-point sources can be further examined to number of points in the array. Okay. So these are the cases, and these 3 cases we have to note down. Okay. First one, the point sources with currents of equal magnitudes and with same phase. Second one, 2-point sources with currents of equal magnitude but with opposite phase. First one, the same phase. Second, we are going to give the opposite phase. And third one, 2-point sources with currents of unequal. You listen here. First 2 cases, we are going to give equal magnitude of current. But in third case, we are going to give as the unequal current with any phase. Whatever the phase, we are going to give. But in the first case, same phase. Second phase, opposite phase. But in the third case, any phase we can give. So based upon these 3 conditions, we are going for the problem. Okay. So in this case, consider 2-point sources 1 and 2. We are going to take 2 more. So 1 and 2 separated by the distance 3. and both the point sources are supplied with the currents equal in magnitude and phase as shown in figure 1. Okay, here you can see figure 1. Yeah, here we have the point source 1. Here we have the point source 2. Here 1 and 2. The distance between two antennas, two power sources is going to be D. The distance between the point sources 1 and 2 is going to be D. And here we have the D by 2. Okay, D by 2, half of the distance. Okay. Yeah. Let point B far away from the array. Here you can see. Yeah. Distant point B. Distant point P. Okay. Let P far away from the array and the distance between point P and point source 1 and 2 be R1 and R2 respectively. Here. R1 and R2 respectively. Okay. Assuming far field observation minus R1, R2 equal to R. Here. Yeah. R1 minus R2 equal to R. Okay. Next. The radiation from the point source 2 will reach earlier at point P than that from point source 1 because of the path difference. Here the main point you have to take about path difference. Okay. That we'll see now. Okay. Okay. This is the diagram. We are going to take two point sources 1 and 2 having the distance of D. At distant point P, we are going to take the value of R1, R2 and R. The phi is going to be called as path difference. Okay. The phi is going to be called as path difference. Okay. The path difference is equal to D by 2 cos phi plus D by 2 cos phi equal to D cos phi. Correct? The path difference can be expressed in terms of wavelength. Path difference is equal to D by lambda cos theta. Just simply we are going to add is the lambda, D by lambda into cos theta. Hence, the phase difference psi is given by, first we have seen the path difference. Next, we are going to see about the phase difference. Phase difference psi equal to 2 pi into path difference. Yeah, 2 pi into path difference. Psi equal to 2 pi into, what is the value of path difference? Path difference is equal to D by lambda into cos phi. D by lambda into cos phi, which is equal to 2 pi by lambda into D cos phi. 2 pi by lambda into D cos phi. We can consider this 2 pi by lambda equal to K. 2 pi by lambda equal to K. At summation we can take beta. K badala we can take beta also. Okay, va? Beta equal to 2 pi by lambda or K equal to 2 pi by lambda. So simply replace that. We are going to get psi equal to KD cos phi. Yeah, psi equal to KD cos phi. And ET, total electrical power, ET equal to E1 plus E2. E1 on the E0 e power j sin phi plus E0 into e power j sin phi. By adding those two things, we are going to get ET equal to 2 E0 cos phi by 2. Yeah, 2 E0 cos psi by 2 minus j psi by 2 plus j by psi by 2. We are going to get cos psi by 2. Okay. So total ET equal to 2 E0 cos psi value. You know about what is psi. Psi equal to KD cos phi. KD cos phi by 2. So this is what about the ET. Okay. The above equation represents total field here. Total field intensity at point P. Correct? Above equation represent total field intensity at point P due to 2 point sources having the currents of same amplitude and same phase. The total amplitude of the field at point P is 2 E0, while the phase shift is KD cos phi by 2. By putting 2 E0 equal to 1, then the pattern is to be normalized to, and given that cos KD cos phi by 2. So by adding this, you are going to get maximum direction. Okay. So maximum direction you are going to get as maximum psi max phi max is equal to 90 or 270. Next minima we are going to get 0 or 120. Okay. So we are going to give the values from this ET. From this ET, we are going to give the value of maximum direction. Okay. Maximum when occur, maximum value of cosine function is plus or minus 1. Minimum value is 0. Okay. Maximum plus or minus 1 ma. So cos KD cos phi by 2 equal to plus or minus 1. So cos pi, KD by 2, we can have D value as lambda by 2. So lambda getting cancelled and 2 value get cancelled and we are going to get pi by 2. Yeah, here also 2 will get cancelled. So pi d, here we have 2. So pi by 2 cos phi equal to plus minus 1. So that you are going to get phi max is equal to 90 or 270. Here it will come 0. By substituting 0, we are going to get minimum direction is 0 or 180. 0 or 180. And half of beamwidth. Half of beamwidth will be existing at 1 by root 2. Root 2. Yeah, 1 by root 2. Okay. So by adding these values, we are going to get phi of HPPD, half power beam width, half power point direction. The half power point direction we are going to get equal to plus or minus 60 or plus or minus 120. So having those values, all the values, maximum direction will occur at 90 or 270, minimum will occur at 0 or 180, half power point direction 60 or 130. Okay, va? 90 or 270, 0 or 180, 60 or 120. By adding all those values, we are going to get the value. So the field pattern drawn with T against 5 for lambda by 2, then the pattern is bidirectional as the figure 2 will be available. The field pattern obtained is bidirectional and is figure of 8. If this pattern is rotated by 360 about axis, it will represent three-dimensional downward shaped space pattern here. Yeah, this one. Okay, wow. Where the maximum pattern will be occurring, maximum at 90 and 270. Where the minimum 0 and 180. Here you can see maximum at 90 and 180, 270. Minimum at 0 and 180. Okay, wow. So maximum, minimum, in between half power point 60 and 120, 120 and 60. This what about the total field pattern of case 1. Case 1, we are going to give equal amplitude current and same phase. Keep in your mind, equal amplitude current and same phase. Okay, this what you are going to get. Okay, next. In second case, currents equal in magnitude and opposite phase. This point mainly you have to consider. Currents of equal magnitude and opposite in phase is going to be called as equal in magnitude and opposite phase. Okay. So in this case also we are going to get ET value. From ET psi value you are going to get, by applying you are going to get maximum at 0 and 180, minimum at 90 and 270, half power point you are going to get, yeah, same 60 and 120. Based upon this you are going to get this type of radiation pattern, or we can call it as total field pattern of the end-fire array. Okay, this shape is going to be equal of end-fire array. The one which we have seen equal current and same phase, here it's going to be called as broadside array pattern. So in broadside array, the radiation pattern is going to be, you are going to get like this, perpendicular to axis. Okay, it's going to be called as figure of 8. But in case of end-fire array, you are going to get the you are going to get the radiation pattern, or we can say it as field pattern. It's going to be get like this field pattern or total radiation pattern of end-fire array in the case of case 2. Equal amplitude and opposite phase. Okay, this is what about your end-fire array concept. Okay, so all together we can simply say it as third one, unequal in amplitude and any phase. By this case you are going to get like this. You are going to get same formula, same thing you have to use. It's also going to be, yeah, here you have to concentrate about the two magnitude and phase angle. Magnitude ET equal to E1 square root of 1 plus k cos phi square plus j k sin phi square. And theta equal to tan inverse of k sin phi by 1 plus k cos phi. Okay, va? This is what about the third case. What is the third case? I told you already, unequal in amplitude and any phase. Unequal amplitude and any phase. Okay, va? So all together we can say that in your equal amplitude and same phase, the pattern is going to be like our broadside array, figure of 8. And in second case, equal amplitude and opposite phase, the radiation pattern is going to be get like this N fire shape. That's going to be called as downward shape. Okay. And third one, unequal amplitude and any phase, you're going to get the shape in case of coincidence with the help of antenna. Next, we are going to see about n element linear antenna. So in n element linear antenna, we are going to take n number of antennas. 1, 2, 3, 4, 5, 6 till n minus 1. Okay. Having the distance of d. D. Here we have the D. Okay. And at the distant point P, we are going to be able to find out the radiation pattern or field pattern produced by the different point sources available in the axis. Okay. Va? So psi is nothing but phase difference between the individual antenna having the value of d cos phi, d cos phi, d cos phi, d cos phi. Okay. With the help of this diagram, we can able to find out the ET value. And finally, wait. And finally, you are going to get our antenna array factor. Array factor is equal to sine n by 2 psi by sine 1 by 2 psi. Okay. Keep it in mind, ma. Based upon this, they will ask the question. They will ask the problem in the case of antenna array concept. Okay. AF, antenna array factor AF is equal to sine n by 2 psi by sine 1 by 2 psi. Okay. Or simply we can say it as ET max equal to E naught into n. Okay. So finally you are going to get normalized array factor. Keep this in mind. Please note down this. Normalized array factor equal to K array factor AF, array factor AF is equal to sine n by 2 psi by n sine 1 by 2 psi. Keep this in mind. Definitely you'll be getting a question like this. Normalized array factor AF of n equal to sine n by 2 psi by n sine 1 by 2 psi. Okay, va? This what? Okay. So first we'll see what is this concept and then we'll go to the topic. An array of element is said to be linear array if all the individual antennas are spaced equal along a line. An array is said to be uniform array if the elements in the array are fed with equal magnitudes and uniform progressive phase shift along the line. Okay, va? Consider a uniform linear array of n isotropic point sources with all the individual elements spaced equally at distance from each other, and all elements are fed with currents equal in magnitude and uniform progressive phase shift along the line as shown in the figure. Okay, so with this figure we can able to clearly note down that how many antennas we are going to use at distant point P. What about the antenna array factor? Don't forget, this is the antenna factor concept. Antenna factor is equal to sine n by 2 psi by n sine 1 by 2 psi. Very important topic. Okay. Next, broadside. I told you already, with the help of array factor, we can able to decide psi equal to kd cos phi plus psi. Because we are going to use n number of point sources in the case of broadside array. Okay. So while we are using the n number of point sources in n number of array, while the consideration of broadside, what is the condition? Anyone tell me what is the condition of broadside? Equal magnitude and equal phase. Don't forget, equal magnitude and equal phase is going to be called as broadside array. Okay, va? So this is what about the broadside array concept. Okay, same here also we are going to minus major lobe nulls, so that we are going to get this, and finally we are going to draw the where's that direction of before that we have to know about the concept of maxima and minima. One second. Yeah, you are going to get Major lobe maximum 90 to 70 as like the first case. Case 1 equal amplitude and opposite phase 90 or 270. Major lobe. Minor lobe. So minor lobe will get 0 and 180. 0 or 180. So by putting all those value, we are going to get the radiation pattern same like this. Yeah. Like this, you are going to get the radiation pattern like our case 1. That's what about the broadside array concept. Next, we are going to see about infrared array concept. Okay. In this case also, yeah, major lobe maximum you are going to get 0 or 180, and minor lobe maximum you are going to get 90 or 270, and finally you will get some formulas. Yeah, this what about. So before that, we'll see the formula. Broadside la. Yeah. So based upon this you will get questions. Okay, va? Beam width between first null equal to 114.6 by L by lambda. Half power beam width 57.3 L by lambda. And directivity, coming to the point of directivity, directivity can be expressed in terms of the total length of the array. D max is equal to 2 into L by lambda. T max is equal to 2 into L by lambda. So definitely, surely you'll get in a question like this. So you simply will substitute the values available for the antenna array concept, L by lambda value here. You are going to get the beam width between first null and half power beam width. Okay, like that for N-fire array. N-fire array you are going to get like this. Beam width between first null equal to 114.6 degree into root of 2 by L by lambda in terms of degree. Similarly, you can able to find half power beam width. The half of the first null beam width is going to be half power beam width. Half power beam width equal to 57.3 degree into square root of 2 by L by lambda in terms of degrees. Okay. And finally, directivity of N-fire array. Directivity can be expressed in terms of total length of the antenna. D max is equal to 4 into L by lambda. There it is 2 into L by lambda in the case of broadside array. But in the case of N-fire array, D max is equal to 4 into L by lambda. Okay. Next, principle of pattern multiplication. Yeah, it's a very important topic. So in the case of principle of pattern multiplication, definitely you can come to know that the points like this. Just listen 1 second. Yeah. The field pattern of an array of non-isotropic but similar sources is the product of the pattern of the individual source and the pattern of isotropic sources having the same location, relative amplitudes and phase as the non-isotropic but point sources. This is referred to as pattern multiplication for array of identical elements. Total field E equal to E of theta comma phi into E of theta comma phi into EPA of theta comma phi plus EPA of theta comma phi. Okay. So multiplication of field pattern into addition of the phase pattern. So total field equal to multiplication of field pattern into addition of phase pattern. Please remember this formula. Okay. With the help of this, you can come to know what is E of theta comma phi, field pattern of the individual source. E of theta comma phi, field pattern of array of isotropic source. Next, EP of theta gamma phi is phase pattern of individual source. EP of theta gamma phi equal to phase pattern of array of isotropic source. Okay, wow. This what about this concept? Yeah, yeah. Here, consider. Yeah, look at this example. Definitely get clear idea about your pattern multiplication concept. Consider a 4-element array of antenna as shown in figure 1, in which the spacing between the elements is lambda by 2 and the currents are in phase alpha equal to 0. Okay, the pattern can be obtained directly by adding the 4 elements filled due to 4 antennas. However, the same radiation band can be obtained by pattern multiplication in the following manner. Okay, yeah, these are the 4 patterns and we are going to get like this. Okay, va? Yeah, the 4 patterns. So 1 and 2 are simplified and put in the mid of 1 and 2. 3 and 4 are simplified and put at the mid of in between 3 and 4. By adding these two, we are going to get the difference is lambda. By the lambda, we are going to get, by adding these two, we are going to get the value of like this. So, individual pattern, group pattern. By multiplying, yeah, what is the result? Resultant radiation pattern of 4 elements, resultant radiation pattern of individual elements. There we are going to get array of 2 points, array of 2 spaces. Okay. So this multiplication, this you are going to get like this. Result pattern of 4 isotropic pattern. Very, very important. Huh? First, 2 we are going to multiply individual pattern due to 2 individual elements into group pattern due to array of 2 isotropic spaces by lambda. You are going to get resultant pattern of 4 isotropic element. Like that, you can also give another example of 8 element. Okay, no need that. You can understand by seeing this one. Okay, and coming to the point of phased array, adaptive array, it's not there in our syllabus. Just to go through. So in this case of this, we are going to see about the concept of Pascal triangle. Yeah, this one is a Pascal triangle. Okay, this is a Pascal triangle. How we are going to get values? Just travel. No need. Till that, you have to know what is pattern multiplication. Okay. So Yagida antenna, I told you, it's one of the example of parasitic array. So this is what about. So this is the formula which are used to find out the length of the reflector, director, and driven element and director. Driven element is dipole antenna. The driven element in the Yagida antenna is going to be called as dipole antenna, and it's going to be reflector antenna, director length. Okay. So what about Yagida antenna? Here you can see. So here the feed only we are going to give for the driven element, not to the reflector, not to the director. R is reflector ma, D are not driven element, D is the director. Okay. So this was the field pattern produced by our Yagida antenna. Okay. So working principle no need, just to go through once. So this is the field pattern, how we are going to get our Yagida antenna. So application I told you, Yagida array is the most popular antenna for the reception of terrestrial television signal. Yeah, I told you. In TV signal reception, we use the terrestrial television signal VHF band 32 300 megahertz. Okay, ma? And these are the short questions which are frequently asking, just to go through once. And now we'll see some problems. Okay, yeah. The antenna array is defined as a system of similar antennas related to get required dash in the desired direction. What is that? எனவே நம்மளுக்கு எதனால ஆண்டனா அரேக்கு போறோம்? We are going to see the antenna array to get the greater gain, greater directivity, greater bandwidth. Correct? So the answer is going to be D. All of the above. All should be high for listening the antenna array concept. Okay. Find the odd element out. Broadside array, end-fire array, collinear array, and finally Yagi antenna. Okay. In this case, D is the answer. Yena broadside, end-fire, collinear array type of antenna array. Okay. Yagi array is a type, a design of antenna is going to be called as Yagi array. How we are going to design Yagi array? Yagi array is going to be designed with the help of parasitic array. Clear? இங்க யாகி அரே வரக்கூடாதுன்னா parasitic array வரணும். அப்ப வந்தாதான் all 4 are the types of array antenna concept: broadside, end-fire, and collinear, and Yagi array. So the answer is D. Okay. The broadside array is defined as an array having maximum radiation dash the axis array, which is A, perpendicular to axis. நம்ம already சொன்னோம். So perpendicular இருந்ததுதான் we are going to get the field pattern in the form of figure of 8. We are going to get the field pattern in the form of figure of 8. Next, the collinear array is also called as broadside, broadfire, omni, and all of the above. So one is the broadcast array, like our broadside array. Okay, broadside array, broadcast array, going to be called as collinear array. The another name of collinear array is going to be called as broadcast array. Okay, the end-fire array is defined as an array having maximum radiation dash the axis array. Okay, along the axis array is going to be the answer. B. ஏன்னா n-fire we are going to get the radiation along the axis of the array. That's what it's going to be called as n-fire array. What is the condition for n-fire array? The condition for n-fire array, sources with equal amplitude and opposite phase. Don't forget this. Sources with equal amplitude and opposite phase. Okay. Next, an array is said to be uniform array if the array elements are fed with equal amplitude and uniform progressive phase shift. Okay, va? An array is said to be uniform array if the array elements are fed with equal amplitude and uniform progressive phase shift. Okay. Next, in a broadside array, the direction of maximum radiation indicated by 90 and 270. In broadside na angle is going to be called as figure of 8. Figure of 8 la maximum direction varum 90 ku 270 ku varum illaya adha paathom 90 270. Here you can see this diagram, 90 and 270. Yeah, you can refer this diagram. Yeah, 90 and 270 in case of broadside. Yeah, next. Yeah, next. The n-fire array, the direction of maximum radiation occurs in where? In the n-fire array, the direction of maximum occurs in where? Again. Sorry. There it is maximum, here it is minimum. Inga maximum edu varudho adha inga minimum varum. So 90 and 270 is the answer. Correct? So whichever the answer we are going to get for 7th problem, maximum 90 and 270, minimum of 90 and 270 for the problem 8. Okay, va? The relation between the directivity and the array factor length is given by D equal to 4 into L by lambda. Don't forget this. D into 4 into L by lambda. Okay, va? In a phase array, the maximum radiation in any direction can be obtained by controlling dash excitation in each element. Okay, va? The answer is phase. Phase excitation in each element. Okay, va? At the end of the topic, students will be able to understand the basic concept of antenna array and the radiation characteristics, to understand the principle of types of antennas and arrays, to get exposure to different types like broadside array and n-fire array, to know the applications of antenna array, example with Yagi-Uda antenna. So Yagi-Uda antenna is the example of parasitic array. Don't forget. Yagi-Uda is the example of parasitic array. Okay. So this what? So these are the topics what we have discussed today, and few of the problems and the major problems also we discussed in this PPT. Okay, va? So before we are going to winding this concept, we have to know that what are the topics we have to see. Okay, va? What are the topics we have to discuss so far? Okay, yeah. Generally, I told you already. What is your antenna? What is the antenna array concept? The topic is antenna arrays. Okay, va? Antenna arrays. Yeah. I told you already. It is a system of similar antennas oriented similarly to get greater directivity. Okay, va? It may also be defined as radiating system consisting of several spaced and properly phased radiator is going to be called as the concept. Next one, general types of this. General types, you have the two types. One is going to be called as linear antenna, linear array, and second one is going to be called as uniform linear array. Okay, va? I'll tell you what is linear. An antenna array is said to be linear if the individual antennas of array are equally spaced along a straight line. Is going to be called as linear array. And in case of uniform linear array, the uniform linear array is one in which the elements are fed with currents of equal magnitude with uniform phase shift along the line. It's going to be called as uniform linear array. And coming to the point of types, I told you types of antenna array. I told you there are 5 types of antenna arrays are there. One is based on geometry configuration. 3 types: linear, planar, conformal. Second one based on current excitation. 2 types: broadside and end fire. Third one based on elements. We have 2 types: parasitic and non-parasitic. And fourth one based on amplitude distribution. We have uniform, binomial, edge, and optimum distribution. And last one based on types of input output signal. We have phased array, retro directive or self focusing array, and third one adaptive array. And apart from that, we have generally 4 types of antennas. One is broadside array, second one end fire array, and third one collinear array, and finally we have the parasitic array. Okay, wow. So the condition for broadside is going to be called as, in broadside all the antennas are equally spaced along the perpendicular to the wave axis, antenna axis. So the radiation you are going to get in the case of broadside array is going to be called as figure of 8. Okay, wow. And in case of second one, end fire array, all the elements are coincides with the antenna array axis, so that the radiation also will be coincides with the help of antenna array axis. So the shape is going to be called as downnet. First one the figure of 8, second one downnet. Third one collinear antenna. In collinear, the antennas are going to be arranged in the form of coaxial type. Okay, wow. So we have 2 types of collinear axis. One is horizontal, another one is vertical collinear axis. And last one parasitic antenna. So what is the main difference between the parasitic and all 3? Broadside, end fire, collinear is going to be like this. So in all 3, individual antenna should be fed. Individual antenna, we have to give the excitation, we have to give the input, correct? But in the case of fourth parasitic array, we are not going to feed all the antennas, but in parasitic array we are going to give only for the driven element. Based upon the driven element value, the reflector and director which is available in the parasitic array, which will be guiding the entire antenna concept. Okay, that's what about the parasitic array concept. Okay, all 4. We have broadside, we have end fire, we have collinear, and we have parasitic concept. Okay, wow. Next, broadside also we have discussed. The diagram also we have seen. So maximum radiation will be called in the form of figure of 8. Next one, end fire. End fire also the direction of maximum will be coincident with the axis of antenna array. Collinear we have 2 types. One is going to be vertical, another one is going to be called as horizontal. Okay, and the next parasitic I told you. So the best example is going to be called as Yagi-Uda antenna. We have the dipole. Dipole is going to be called as driven element. We have the reflector and we have the director. So we are going to feed only the dipole, driven element. So based upon feeding towards our dipole, all elements will be excited and it's going to be acting like our antenna. Okay. And also we discussed 2 point sources. 3 cases are there. 3 cases very important. Okay. The first one is going to be called as 2 point sources with the current of equal magnitude and with same phase. Second one, 2 point sources with currents of equal magnitude but with opposite phase. Third one, 2 point sources with currents of unequal magnitude with any phase. So based upon these 3, we are going to design the factor. This is the arrangement of one of case 1. And in case 1, you are going to get the radiation is going to be like this. Yeah, case 1, equal in amplitude and phase. Same like our broadside. Case 2, equal in magnitude and opposite in phase. Okay, there we are going to get the field pattern like this. Similar like our end fire. Okay, wow. And case 3, unequal in amplitude and any phase. It's also similar towards your end fire concept. Next, n element. We are going to use n element. In this case, number of elements we are going to use. At distant point P, we are going to be able to find out the field pattern with the help of the antenna array factor. Okay, this point you have to remember. Now antenna array factor. Okay, wow. Equal to sine n by 2 psi by n sine 1 by 2 psi. Okay, wow. This one about the concept. Next, we have seen broadside array concept and how it's going to be get and the formula to find out the half power beam width and fractional beam width and directivity. Directivity equal to 2 into L by lambda. N fire array. N fire array also similar. We are going to get broad beam width between first null and half for beam width, and directivity equal to 4 into L by lambda. And the principle of pattern multiplication also we discussed, and how we are going to get. Example, we took the 4 element concept. So in 4 elements, we are going to make it as a 2 element, so that you are going to get the multiplication of individual element with group. You are going to get the resultant pattern. Okay, individual pattern into group pattern, we are going to get the resultant pattern of the 4 isotropic element. Okay, so that's what phased array adapter thevalama. You need not study, just simply I have added this concept. Okay, in these cases we are going to get like this. Pascal triangle will come, so that the formulas are going to be more helpful. Okay. Next, Yagi antenna, the best antenna for the parasitic array concept. Okay. This is the design of Yagi antenna. We have the divided element, reflector, and director. This is the radiation pattern of the Yagi antenna. Yeah, here also the radiation pattern will come. Okay, this is the radiation pattern of Yagi antenna. So I told you it's mostly useful in the case of television signal reception, purpose. Okay, va? And these are the short questions, and we have discussed the problems also from this slides. Okay, discuss those slides, and after that you can come to know what is antenna array concept in detail. Okay, so these are the topic, these are the things which we have discussed today. Okay. So this is what about your antenna introduction to antenna array concept. Introduction to antenna array concept. Okay. So mostly you have to concentrate about your broadside, end fire, and collinear and parasitic. So be clear with the formula. Be clear with the formula about your broadside, end fire, collinear, and parasitic array. So by simply knowing the formula, by substituting the values, whichever the values given in the problem, by substituting those values in the formula, you can get the idea. You can get the proper result. Okay, va? So prepare well for the exam, for GATE exam. All the best for the GATE exam. Best of luck. You can write your exam well. Okay, va? Not only my subject, all subject you plan, prepare accordingly. You plan it for all subject and prepare it for the exam properly. Okay. So these are the cases what we have discussed. So from the basic, we discussed about what is the fundamental parameters of antenna. So the fundamental, what we know that before that we started with wired communication, wireless communication. Then only we can come to the point of antenna concept in the form of wireless communication, and the concept of fundamental parameters like radiation pattern, beam solid angle, radiation intensity, gain, directivity, polarization, effective aperture, antenna temperature, antenna resistance, front to back ratio, everything we have seen. Okay. Apart from that, also we have discussed the what do you mean by dipole and how the radiation pattern, how the dipole antenna will be radiating the energy in the form of EM waves, and also monopole. Monopole is like our dipole antenna. It won't have the opposite pole. In opposite, we are going to place the ground. Okay, that's what about the monopole. In dipole and monopole, you have to concentrate about the field parameters, directivity, gain, effective aperture, everything. Formulas you have to find out. You have to know about. Okay, later on that you should know about your monopole formula also. You have to know. Okay, so in your dipole, sorry, in your dipole antenna, the thing what you have to understand is going to be called as field components, electric and magnetic field component, and also you have to know about your power radiated, radiation resistance, effective aperture and directivity. Effective aperture and directivity, you have to know about those parameters and those formulas. Okay, so be clear in formula. Generally, you can answer all the questions. Okay, like our dipole antenna also, power radiated PR equal to 40 pi square I naught square L square by lambda square. Radiation says RR equal to 80 pi square L by lambda whole square. Effective aperture 0.119 lambda square, and directivity of dipole antenna, short dipole antenna is equal to 1.5. So the directivity of your directivity of lambda by 2 antenna is going to be equal to 1.63. Okay, for isotropic it's 1. Okay, isotropic directivity is 1. Short dipole directivity is equal to 1 by 1.5. Half wave dipole directivity is equal to 1.68. Keep those values in your mind. Definitely you can get the question from this concept. Okay. So these are the topics we have discussed. And apart from that, we discussed the antenna array concept. In antenna array concept also, you have to mainly concentrate what is antenna array, what is linear array, what is uniform linear array, what are the types of antenna array based upon the construction. Next, based upon the types, in types also you have to concentrate about your broadside array, end-fire array, collinear array, and parasitic array. Those things you have to concentrate. And finally, you have to know about your what is formula to find out the directivity, half per beam width, fractional beam width in all those cases. Okay. And also you have to consider about n element array, and in the case of pattern multiplication. Pattern multiplication concept also very important in the case of antenna array concept. Okay, generally we covered all the topics whatever the syllabus given in GATE. We have covered almost all the topics along with fundamental also we covered. Okay, because fundamental is the main thing. Whatever the combination you go, the fundamental concept is very important. Okay, so we have seen what is fundamentals, what is dipole, what is monopole, and what is antenna array concept. Okay, with this I can conclude my speech. Thank you, students, for attending our GATE class.